Today we're going to be looking at drawing Lewis structures to represent the structure of a molecule. We're going to be looking at the information from the first page of notes that you have on a PowerPoint slide. It's called Representing Molecular Model Notes. You're going to want to fill those in. I'm also going to be doing about half of the examples from the back. What I would advise is that you have a piece of paper ready to actually draw out these examples as I go through them. And then you can just take a picture of those along with the other ones that you do on your own to just upload to that PowerPoint presentation rather than trying to draw them within Google Drawings. So if we get started, when we are trying to represent Lewis structures, the first thing we need to do for our compound is count the number of valence electrons that'll be in our picture. And to look at that, we're first going to start with something like NH3, which is actually an ammonia molecule. We know the number of valence electrons in each group on the periodic table. We're just looking at that main block. So that's groups 1, 2, and then groups 13, 14, 15, 16, 17, and 18. Remember, the number of valence electrons just goes up as you go across, so 1 all the way through 8. Since nitrogen is in group 15, that's going to have 5 valence electrons. And then since hydrogen is in group 1, each of them will have 1 valence electron. So we take 5 plus the 3 times 1, we multiply the subscript times the number of valence electrons for that, and that gets us a total of 8 valence electrons. That's how we know how many electrons need to be in our picture by the end. The next thing we do is choose a central atom. Central atoms are the ones that like to make the most bonds because all the terminal atoms will be attached to them. In order to figure out how many bonds an atom likes to make, we're going to look at the number of the charge, but it's going to be the absolute value of the charge. So group 1 likes to make 1, group 2 likes to make 2, group 13 likes to make 3, 14 likes to make 4. But then we turn back around. Group 15 likes to make 3, then 2, then 1, then 0. There are some special cases though where we actually have noble gases involved in bonds. And if that is the case, then the noble gas that's in the bond automatically gets to be the central atom. Also, if there's a tie, meaning more than one element likes to make the same number of bonds, then the element with the lower electronegativity is going to go in the middle. If you want to look and see exactly what the electronegativity of an atom is, you can look down here, which is on the back of your periodic table. This gives you a number for each electronegativity value, which might be a little bit easier than trying to rank them based on the trends. So if we go back to our example, we had NH3. We know that nitrogen likes to make 3 bonds. Each hydrogen likes to make 1, so the 3 wins, which means nitrogen gets to be our central atom. After we know which one's in the middle, we just arrange all of the other terminal atoms around the center. So basically that means we put the 3 H's in positions around the nitrogen. Think of positions as being up, down, left, and right. These usually don't make big chains. It's usually the center atom and then everybody else goes somewhere in a circle around him. Once we have our atoms placed, we're going to put bonds and pairs. These are called lone pairs, also known as non-bonding electrons, around our atoms. Basically, we just want to draw a line between the center and atom and each of the terminal atoms. We then want to put these lone pairs, these dots in, but only around elements in groups 14 through 18. So that's actually why I erased it from hydrogen, because hydrogen's in group 1. We only put dots if it's from 14 through 18. So really, nitrogen's the only one that gets dots, and he gets dots because he didn't already have an octet. He only had 2, 4, 6, now he's got 7, 8 electrons. Hydrogen, because he's in group 1 through 13, he's perfectly satisfied with whatever bonds he gets, so you never put dots around anything in groups 1 through 13. The last step for most of these is then just going to be verify the number of electrons in the Lewis structure. Make sure that it's equal to the number of valence electrons that we counted in step 1. So at this point we count. Each bond is worth 2 electrons, so that's 2, 4, 6. Each dot is worth 1 electron, but they always come in pairs, so I usually count them together. 2, 4, 6, 8 equals the 8 from an initial count, which means that this is the official Lewis structure for ammonia. This is what you should have drawn on a piece of paper to take a picture of later to insert into your notes. And then we're going to do another example together. For our next example, we'll look at something that has 3 elements. So this is CH2Cl2, carbon, hydrogen, and chlorine. We're just going to practice doing these steps together again. So first thing, count valence electrons. 4 plus 2 times 1, because there's 2 hydrogens, each of them having 1 valence electron, plus 2 times 7. There's 2 chlorines, each of them has 7 valence electrons. So that's 14, 15, 16, 17, 18, 19, 20. Total of 20 valence electrons. Step 2, choose the central atom. Carbon likes to make 4 bonds. Hydrogens each like to make 1. Chlorines also each like to make 1. Make sure you're looking at the number of bonds, not the number of valence electrons for that second step. Carbon likes to make 4 bonds, so he's going to go in the middle. And then we're just going to arrange the terminal atoms around him. It really doesn't matter what order you put them in. It doesn't matter if you put the chlorines next to each other or across from each other. Same with the hydrogens, makes no difference at this point. We put our electrons in by putting bonds between the center and the terminal atoms. And then we give any element that's in group 14 through 18 an octet, which basically means it just needs electrons up, down, left, and right. This chlorine already had electrons over here, so we could put electrons in the other 3 places. Same with this chlorine. The hydrogen's in group 1, so it doesn't get any dots, and the carbon already has an octet, 2, 4, 6, 8, so he also doesn't need any electrons. We count the number of electrons in our picture. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Because the 20 electrons match the valence electrons we have in the beginning, we know that this is an appropriate Lewis structure. The next structure we're going to look at together also has 3 elements. This time it's carbon, hydrogen, and oxygen. So again, start up top, we count the valence electrons. 4 plus 2 times 1 plus 6. 6, 7, 8, 9, 10, 11, 12. We choose the center atom. Carbon likes to make the most bonds, so he's going in the middle. We arrange the other elements around the carbon. 2 hydrogens, 1 oxygen, and then we place electrons in our structure. We've got our 3 bonds drawn here. We look and see which of these need an octet that don't already have one. So hydrogen doesn't need an octet, he's okay with just his bonds. Carbon needs an octet, he's in group 14. He already has 2, 4, 6, so he gets 2 more electrons. And oxygen is in group 16, also needs an octet. So far he's only got 2 that count for him, so we actually give him 6 more electrons. And then we count our electrons. 2, 4, 6, 8, 10, 12, 14. So here we have 14 electrons. And this is the first time where we see that it doesn't match the number of valence electrons that we were supposed to have. And this is where we then go to the remainder of our steps. If the Lewis structure doesn't have the right number of electrons, oftentimes that means you have too many in your picture, too many in the Lewis structure compared to the number you're supposed to have. When that occurs, it actually just means you need a multiple bond. That could be double bonds, that could be triple bonds, or it could be double and triple bonds. In order to create a multiple bond, you're going to erase 2 dots off the center atom and 2 dots off of one of the terminal atoms. Now, you could really erase it off of any terminal atom that has dots if need be, but keep in mind, sulfur, phosphorus, oxygen, nitrogen, and carbon, these are the elements that really like to get double bonds. We call it spunk. Those are the ones that you should erase the dots from first if you have that as an option. Here we really didn't have an option, it was just carbon and oxygen that had dots. And then all we need to do is replace those 4 electrons with 2 electrons by adding a second line. So if you think about it, we erased 4, we added in 2, which means every time you do that, you really get rid of 2 electrons. It doesn't mess up the octets. Notice carbon still has 2, 4, 6, 8. Oxygen still has 2, 4, 6, 8. But now we can do it in less total electrons. 2, 4, 6, 8, 10, 12. That's how many we were supposed to have. So this is the appropriate Lewis structure for CH2O. Occasionally you're going to get some examples where there's actually too few in your picture. We'll get to some of those later, but for right now, just keep in mind, if you don't have enough electrons in your picture, you just add more dots to the center atom, which creates what we call an expanded octet. It just means more than 8 electrons. Any element in group, or I'm sorry, in period 3 or lower can get an expanded octet because they also have those d orbitals. Remember the dungeon, the transition in the middle? They have those d orbitals that they can also use within bonding if they need to. All right, let's try another example. The next example we're going to look at is from the back of your paper, and it's called magnesium bromide. Now here's an example where you aren't given prefixes within your name. I have a feeling that's going to go off, but that's okay. Magnesium bromide. If you aren't given prefixes, remember you are going to have to consider charges. So the magnesium has a charge of +2, bromine has a charge of -1. So the formula for the structure we're going to actually make is MgBr2. We're going to crisscross those. Magnesium bromide, MgBr2. Once we have our formula though, our steps are right back to where they were. 2 valence electrons plus 2 times 7. It's a total of 16 valence electrons. Magnesium likes to make 2 bonds, bromine only likes to make 1, which means the magnesium is going to go in the middle. We put lines between them. Magnesium's in group 2, so it doesn't get any dots, but bromine's in 17, so they do need an octet. And then we count our electrons. 2, 4, 6, 8, 10, 12, 14, 16. 16 electrons, that one's good to go. We've got sulfur dioxide. 6 valence electrons plus 2 times 6 again. That's going to be a total of 18 valence electrons. Here, sulfur and oxygen are actually within the same group. They like to make the same number of bonds, and when that happens, then we're actually going to put the one that has the lower electronegativity in the middle. So sulfur's electronegativity is 2.58. Oxygen is 3.44, sulfur gets to go in the middle. We put an oxygen on either end. It doesn't matter if we go up, down, left, right, up, left, it doesn't matter. And then we give dots to everybody that wants dots. We're left with this picture. We count our electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We're only supposed to have 18, so we erase 2 off the middle, 2 off of one of the other elements, and remember, the elements Spunk like them the most if you have a choice. Here we didn't, they were both oxygen. And then we put a double bond between them. 2, 4, 6, 8, 10, 12, 14, 16, 18. Now interestingly enough, because both of these are the same, you easily could have erased it from the other side instead. And these are actually 2 different structures. These structures are called resonance structures. It just means that a bond has been moved. And that's something that if you come back and take Chem 2 with me, then we're going to go through those a little bit more. But for now, I would accept either answer. Let's look at hydrocyanic acid. That's HCN. 1 plus 4 plus 5. It's a total of 10 valence electrons. Carbon likes to make 4 bonds, hydrogen likes to make 1, nitrogen likes to make 3. Carbon goes in the middle. Anything in group 14 through 18 needs an octet. And then we count electrons. 2, 4, 6, 8, 10, 12, 14. And we're only allowed 10. We erase 2 off the center, 2 off of something else. Put a line between the 2 we erased from. 2, 4, 6, 8, 10, 12. Still need to get rid of 2 more, so we erase 2 more off the center, 2 more off of the nitrogen, and now we have a triple bond. Triple bonds are a little bit shorter than double, which are a little bit shorter than single bonds. They're also the strongest. This would be sharing 6 electrons, which is actually much stronger than just sharing 2. 2, 4, 6, 8, 10 in our picture, 10 in our count. That one's good to go. The next one we're going to look at is actually an organic molecule, And really the only reason that I'm throwing this one in here is because you might see a couple of them in your textbook. And you'll also definitely get them if you come back to me to take Chem 2. When you have an organic molecule, something that has more than one carbon within it like this, it's going to actually form a chain. So you kind of wind up with 2 center atoms. And then the hydrogen, we're just going to evenly split between them. We give everybody an octet that needs an octet, and then we count our electrons. Now keep in mind, carbon was up here in group 14, so that has 4 valence electrons. We have 2 of those. And hydrogen each has 1 valence electron. We have 2 of those. So that's a total of 10 that we should have, but we actually have 2, 4, 6, 8, 10, 12, 14. I'm sure by now you realize what that means. We need to start erasing from something that has electrons, lone pairs, non-bonding electrons that we can use. 2, 4, 6, 8, 10, 12. Still not quite there, and that's where we wind up with this triple bond. You're not going to have any of these on the quizzes or the tests, but you will see a couple in your textbook. And like I said, when you come back and take Chem 2 with me, we'll definitely take a look at more of those now. The next one that I want to talk to you about is diatomic oxygen, which is just a fancy way of just saying O2. When we count our valence electrons, we have a total of 12. And some people then get thrown off when they start drawing the structure because they say, well, which one is the center atom? It really doesn't matter. When you only have 2 elements like this, 2 atoms like this, then really you could think of either one of them as being the center, or you could even think of it as there not being a center. It doesn't really matter. The actual process is the same. We put dots everywhere that it needs dots. We count 2, 4, 6, 8, 10, 12, 14. We realize we have too many. Erase 2 and replace. 2, 4, 6, 8, 10, 12. That would be your Lewis structure for diatomic oxygen. We definitely do want to look at least one example of a polyatomic ion. So something like PO43-. That's phosphate. And remember, those polyatomics are listed for you up here if you forget any of the formulas. Phosphate, PO43-. The actual process of drawing a Lewis structure for phosphate is really not much different than any other Lewis structure. We still need to find each of the elements to figure out how many valence electrons they have. And then we just need to consider the charge. This became a -3 charge by gaining 3 electrons. So we're just going to add the 3. We're doing the opposite. It said -3, we're adding 3, and that'll put our valence electron count actually higher than it would have been. So 6 times 4, that would be 24, 25, 26, 27, 28, 29, 30, 31, 32. After that, we actually have the exact same process that we would have used before until the very, very end. We pick our center atom based on who likes to make the most bonds. We put the terminal atoms around. We give 8 electrons to everything in group 14 through 18. And then we count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. That is the correct number of electrons, so this is a good structure. The only other thing we do for polyatomic ions is we put them in square brackets at the end and put the actual charge up here in the upper right hand corner. So if it's a -3, we write a -3, but that really means we added 3 electrons to the structure to make it work. If you did have a positive charge polyatomic ion, then in this step you would have just subtracted instead of added, and then you would have put the plus whatever charge up here. The last example that I want to do with you together right now is xenon tetrachloride. And I want to do this example because it has a noble gas, which kind of takes us back to this. If a noble gas is involved, it is the central atom. Even though it doesn't like to make bonds, if we're putting it in a molecule, it gets to be in the middle. We count our valence electrons. That'd be 28, 29, 30, 31, 32, 33, 34, 35, 36. And then we put our noble gas in the middle. We spread our terminal atoms out around them. We give everybody an octet that wants an octet. And then we count our valence electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We were supposed to have 36. And this is one of those other examples of not the right number of electrons. If you have less electrons in your picture than what you're allowed, that's when you just add more pairs of dots to the center atom. So that would be 34, 35, 36, just like that. And then that would be the correct Lewis structure for xenon tetrachloride. It can have an expanded octet, meaning more than 8 electrons, because it's below period 2. Anything in period 3 and below can have those expanded octets. Now what I would like you to do is look at the list on the second slide of the Google slideshow for all 20 of the molecules that we're supposed to be covering today. We've actually done 10 of them together, and you can pause this video, replay this video, do what you need to do to get those 10 down. But I'd like you to also draw on a piece of paper the other 10. Once you have all 20 of your Lewis structures drawn, just insert a picture from your phone onto that second slide, and then after you fill in all the blanks on the first page, go ahead and submit that to Google Classroom. At that point, you can then go back to our daily agenda and figure out what else you need to work on. Hope that helped. Email if you have any questions.